Welcome to the 24th and final lecture in our course on quantum mechanics. This course has been a journey into an extraordinary country, the realm of microscopic physics, the realm of quantum mechanics. We've seen how the 19th century synthesis of classical physics was overturned in the first decades of the 20th century and replaced by a new view of nature, quantum mechanics. We followed the struggles of the physicists of that time as they came to grips with the concepts of the new physics. And perhaps we've struggled a bit ourselves to master the abstract language of states and superpositions and amplitudes. We've explored some of the scenic byways of quantum mechanics, taking a look at the behavior of identical particles, at quantum entanglement, at virtual particles, and the physics of the quantum vacuum. And we've looked at some more recent developments linking quantum theory to the idea of information. We've learned some of the basic rules governing quantum information, and we've talked about how quantum communication and quantum computing can accomplish tasks that would otherwise be impossible. The quantum realm is a wonderfully strange place. Indeed, we are not entirely sure just what kind of a place it is. There is significant disagreement about the meaning of quantum mechanics. There are rival schools of interpretation, and we discussed three of them: the Copenhagen interpretation, the hidden variables interpretation, and the many worlds interpretation. So in this final lecture, I would like to reflect on what it is that makes quantum mechanics so strange and so mysterious. A little of the answer, I think, is sheer unfamiliarity. The quantum realm is very far from our everyday experience. It's far away, not in distance, but in size. So it's bound to be surprising. But there is more to it than that. I think that there is a thread running through all the bizarreness of quantum mechanics, a common theme that shows up again and again, sometimes in an obvious way, sometimes disguised. I think this is the very thing that gives quantum mechanics its enigmatic quality. What is that theme? Well, let's return to the example of one photon in the Mach-Zehnder interferometer. This has been our prototype quantum experiment, our conceptual laboratory for exploring ideas. It's where we return when we want to probe our perplexities. The interferometer is all about interference, and interference challenges our intuition. If we block either beam in the interferometer, then either detector might register the photon. If we leave both beams open, only one detector can possibly click. And this is because of constructive and destructive interference of quantum amplitudes, or of the quantum wave, if you prefer that language. So, when can interference between the two paths occur? The answer is when there is no measurement. If we make a measurement of which path the photon takes, even with super non-destructive photon detectors, the interference effect goes away. And what do I mean by a measurement? I mean the formation of any physical record anywhere of which path the photon takes. Measurement is not so much about conscious observers as about the rest of the universe. And so in the interference experiment, when interference is happening, that means that no physical record is being made anywhere in the universe of which path is being taken. No forensic examination of the interferometer or its surroundings could later establish what happened exactly, which way the photon went. And that's an astonishing claim. The photon makes its journey through the interferometer under conditions of absolute secrecy. It's all about information. The photon is informationally isolated during its trip. No information leaks into the rest of the universe. The magic of quantum interference between paths happens if, and only if, it is impossible in principle to determine what path is taken. And this is just what we mean by the photon travels both paths through the interferometer. Okay, this is the Copenhagen sort of language. So how would we describe this in hidden variables language? Well, the quantum wave, says the hidden variables interpretation, the quantum wave spreads throughout the interferometer, and any measurement apparatus will affect this wave. And if I don't make a which path measurement, then we have wave interference at the second beam splitter. And the quantum particle actually follows one path through the interferometer, guided by the wave. That's the interferometer experiment in hidden variables language. All right? How would I describe this experiment in many worlds language? Well, when the photon enters the interferometer, the state of the whole universe branches in two. But in a sense, this is a very tiny branching. It only involves one photon. It's still possible at this stage to bring the branches back together, which is exactly what happens at the second beam splitter. Interference, in fact, means bringing the branches of the universe back together. So, if we interact with the photon to determine its path, then the branching in the universe involves not just the photon, but lots and lots of other stuff. The apparatus of our measurement, our memories, the atoms and photons in the local environment. All are involved in that splitting. And so, in a sense, Humpty Dumpty has broken. And all the king's horses and all the king's men cannot put the universe back together again. The branching in the superposition is now effectively permanent. So the moral of this is that interesting and meaningful statements in one interpretation of quantum mechanics actually correspond to interesting and meaningful statements in the other interpretations, although mostly the meanings are quite different. From now on, I will mostly adopt Copenhagen language for talking about quantum mechanics. It's the most directly connected to our experience of the quantum world. So I find it easiest to talk that way. Let's go back to the idea of informational isolation. Quantum interference only happens when the photon travels through the interferometer in secret. So if you want to put it into a slogan, you might say that quantum mechanics is what happens when no one is looking. I think it's a slogan suitable for a t-shirt. Or put it another way, quantum mechanics is like a trick in a magic show. Imagine a stage magician has a trick box, and in it he puts a couple of eggs, and he says, abracadabra, and he pulls out a bunny. We go, amazing, that's fantastic, we applaud. Now, but for that trick, we believe that if we could peer inside the magician's box, we could find out how the trick works. We could find out that there was a secret compartment in the box, or there was a trap door or something like that. If the box were open, or its walls were somehow transparent, then we would be able to see how the trick is done. Now, the quantum magic box is different. The interference trick only works when the box is absolutely closed. If we open the box and look inside while doing the trick doesn't work. A closed box is a necessary part of the interference trick. Even in principle, therefore, we cannot find out how it's done. Of course, we can learn to do the trick, to predict what will happen. And that's exactly what quantum mechanics, the theory of physics, is for. Quantum mechanics is full of strange mathematical abstractions. It's full of states and amplitudes and so forth. There are rules about superpositions, about probabilities, about how the state changes, rules about the composition of states. And we can learn to use quantum mechanics and learn to do some amazing tricks. And we've seen a few of those. But the magic in the box remains mysterious. because that magic must remain hidden. The hiddenness is part of the magic. That's why quantum mechanics is so elusive. It only happens where we can't see what is happening. We're really coming close to the heart of the whole business. One of the most magical things that we have considered is quantum entanglement. John Bell showed us that quantum mechanics is incompatible with our natural, common sense, intuitive ideas about the world. That was Bell's theorem. We saw that quantum mechanics violates Bell's inequality, which must hold true in any world governed by local hidden variables, any world which is governed by tiny deterministic instructions that function locally. The relationship between two entangled particles simply cannot be explained by supposing that the particles act independently based on a prior agreement. Now, what I want to tell you now is something else, another property of quantum entanglement that I haven't mentioned yet. And that is that entanglement is an exclusive relationship. Suppose you have particle 1 entangled with particle number 2. If particle 1 is entangled with particle number 2, that means that it is not entangled with particle number 3 or particle number 4 or particle number 5. There's actually, to do the math carefully, there's actually a trade-off. The more entangled number 1 is with number 2, the less entangled it can be with number 3 or number 4 or number 5. And if we have two spins in a total spin 0 state, an E-bit, those two entangled spins are entangled to a maximum degree, and neither of them can be entangled with anything else in the universe. The relationship between them is absolutely unique. The entanglement of quantum particles is not simple correlation. For example, my newspaper happens to be correlated with your newspaper. When we compare them, we find they have exactly the same stories in them, exactly the same pictures, exactly the same ads. They're correlated to the maximum degree, but that does not mean that my newspaper therefore cannot be correlated just as much with other newspapers. There can be a great many newspapers that are all maximally correlated together. The relationship between your newspaper and mine is in no way unique. Now remember what the difference is between classical and quantum information. Quantum information cannot be copied. That was the quantum no cloning theorem. Well, for entanglement, we have a kind of quantum information. We measured it actually in E-bits. And no duplicate of particle number 1's relationship to particle number 2 can exist. This entanglement between 1 and 2 is a totally private relationship. The rest of the universe is excluded from sharing it. And this is actually a deep principle of quantum information theory. It's called the monogamy of entanglement. Now I want to tell you something wonderful and actually quite new. Bell's theorem and the monogamy of entanglement are actually closely connected. It turns out that they are two sides of the same coin. So, to state it more carefully, two entangled particles can violate Bell's inequality only because their relationship is exclusive. Put it another way, relationships that can be shared with others, mere correlations, like the correlations between two editions of the same newspaper, can always be explained by a common sense sort of theory, a theory in which there are hidden variables in the world that function locally. So what Bell's theorem really tells us is this: pairs of entangled particles have a relationship that is totally private. And this relationship cannot be shared with anything else in the entire universe. We on the outside cannot, in principle, see inside the relation between two entangled particles. This is the very thing that allows the particles to cooperate with each other in such a surprising fashion. I'm very fond of Abner Shimoni's description of quantum entanglement. Not action at a distance, but passion at a distance. A very exclusive and private passion. These things are possible in the microscopic quantum world. What about the macroscopic world, the world of our everyday experience? We can observe quantum interference in a photon or an electron. Why is it hard to observe quantum interference in a baseball? After all, a baseball is made of atoms. A baseball is made out of quantum systems. Now, the answer isn't simply because large objects are more massive. The answer is more subtle than that. The reason that we can't see interference effects in large objects like a baseball is that large objects are exceedingly difficult to isolate from the outside world. Remember, to see the interference in the photon experiment, we needed to make sure that the photon was informationally isolated from the outside world. What would it take to do the same thing for a baseball? What would it take to make sure that no record is made anywhere in the universe of which path the baseball follows? Well, let's see. To begin with, we're going to have to remove all photons and gas molecules from the experiment. Because as the baseball flies through space, if a gas molecule bounces off of it, that gas molecule will have recorded the presence of the baseball. And the same thing for photons. If a stray photon of light reflects off of the baseball, that's a measurement. That means later on, someone examining the photons in the room could tell where the baseball was. So we're going to have to eliminate the gas molecules and the atoms in the room. We're also going to have to cool the baseball very, very close, fantastically close to absolute zero. Why? Because if the baseball has any appreciable temperature at all, it will itself emit photons, blackbody radiation. And those photons will carry an image of where the baseball is located. So we're going to have to cool the baseball really, really cold. We're going to have to worry about all kinds of things, because we're going to even need to worry about how the gravitation of the baseball, fantastically small as that is, affects nearby atoms. Why are we going to have to worry about all these tiny, tiny details? Because any information leakage, even information leakage into one atom of the environment, destroys the interference pattern, because that makes a record that could, in principle, later be read to determine which way the baseball traveled. And because that is so very, very difficult, it's practically impossible to do an interference experiment with a baseball. What's the fundamental point? The fundamental point is that macroscopic objects are very, very strongly connected to the rest of the world. If you will, they are the celebrities of the physical universe. Their every move is watched by the atoms and photons around them. Therefore, there's no possibility of interference. And their relationships are a matter of public record. And that means there's no possibility of entanglement between macroscopic objects, because entanglement is a purely private relationship. Now, if we're careful, we can observe interference for photons, for electrons, atoms, and so on. But we cannot cut a baseball away from the rest of the world. We can't close the lid on the magic quantum box. So we can't do the trick. The hiddenness of quantum processes, their inaccessibility to our gaze, is not just an inconvenient fact. It's the central point in the whole thing. John Wheeler introduced a beautiful metaphor for the nature of quantum mechanics. He said that quantum mechanics is the great smoky dragon. The dragon's tail appears at the start of the experiment. The dragon's head bites one of the particle detectors at the end of the experiment, and in between, the dragon is shrouded in smoke. We can never say exactly where it is or what its shape might be. The great smoky dragon represents the basic elusiveness of the quantum realm. And Wheeler's great smoky dragon lives in every part of quantum mechanics, in every part of the microscopic realm. The dragon is shrouded in the uncertainty principle, and it's shielded by the principle of complementarity. And it has a remarkably delicate touch, in fact. It can tickle a hair trigger bomb without setting it off. What about a pair of identical particles? Well, that's not exactly like two separate dragons. We can see here are a couple of tails, there are a couple of heads, but which tail goes with which head? In between, there's only smoke. So two identical particles behave more like a single dragon with two tails and two heads. Nevertheless, Feynman's ribbon trick does give us a hint about how the dragon twists among the particles with spin. So we can say some things about the smoke. Now, in Feynman's view of quantum mechanics, the sum over histories approach, you'll recall, the dragon gets from here to there by wriggling through everywhere in between. The dragon is actually everywhere in the smoke. And this has a number of amazing consequences that we followed. For example, it seems that virtual dragons stretch invisibly, concealed altogether by the smoke, between particle and particle throughout the universe, carrying forces between them. That's how the forces act between elementary particles. And even in places where space appears empty, it really isn't. It's like one of those old maps where the blank places have the inscription, "Here there be dragons." Even when space appears to be empty, the quantum vacuum is still alive with zero-point energy, with the stirrings of the quantum dragon. And then there's quantum information. Quantum information reminds us once again of Wheeler's great smoky dragon, for it cannot be pinned down. It cannot be copied. But the dragon of quantum information can be tamed. We can train the dragon to do our bidding. We can use the dragon to help send secret messages that no eavesdropper can penetrate, because no eavesdropper can penetrate the smoke of the great smoky dragon. And we found that dragons carry their messages in strange ways, even snaking backward in time. Although we can't quite catch them snaking backward in time, but it seems that they're doing that. And we also found out that we can educate the dragons considerably. In a quantum computer, the dragon can be persuaded to solve extremely hard math problems, and to do it very, very rapidly, completely inside that veil of smoke. But entanglement, I think, is the most dragonish aspect of quantum mechanics. Entanglement is a relationship between quantum particles that is so exclusive, so private, that it cannot be shared with others. So it turns out that our great smoky dragons are monogamous. Now, the Great Smoky Dragon is really a Copenhagen picture of quantum mechanics. And that's really no surprise, because Niels Bohr was John Wheeler's mentor. And I guess it's also no surprise that I find the picture of the Great Smoky Dragon so compelling, because Wheeler was my own teacher, my own mentor in the ways of the dragon. So here's a picture of me with the Great Smoky Dragon. This is actually a print in a Chinese restaurant near my home. I like this print especially because an actual quantum mechanics discovery was made right there. It was a problem in quantum information theory that we had been working on for years, and one day at lunch, my friend and collaborator Mike Westmoreland found the last piece of the puzzle about 2 yards away from this picture of the Great Smoky Dragon. So I find this picture doubly inspiring. They say that Chinese dragons are especially beneficent. All right, in Copenhagen terms, the tail and head are the places where the dragon emerges into the macroscopic realm, the realm of classical physics, the world, the only world that we can unambiguously call real. And it's the smoky in between where we have the indescribable quantum realm. But of course, other interpretations of quantum mechanics are going to deal with the dragon in other ways. The hidden variables interpretation says, yes, the dragon does have a definite shape. On the other hand, the shape of the dragon is exceedingly strange, because parts of the world that seem far apart are actually close together on the dragon, influencing each other. Because in the hidden variables interpretation, distant parts of the universe have inseparable connections, inseparable influences. In the many worlds interpretation, the dragon has no tail. The dragon has no head. Everything is inside the smoke, including us. When we think we see a tail or a head, we are actually only seeing a tiny part of the whole dragon, which encompasses every possible quantum world. Now, in my view, none of these make the quantum dragon any less mysterious, because the dragon's mystery is the one certain and inescapable aspect it has. So, we have reached the end of the course, our journey into quantum mechanics. There is much that we have not explored. There's much still to learn. Indeed, I have to tell you, there is much still to be discovered about the quantum realm. I hope you found this journey as exciting, surprising, challenging, mind-stretching, and wonderful as I have, and as I do.